For this integral, we have e theta cos theta d theta. Now, none of these, we don't have any common integral involved in here. There's no substitution we can apply, so we should maybe look at parts. And since it's a product, we can maybe try parts on this. So again, the key to parts is know that there's a formula, and what the formula does is just gives us a rearrangement such that we have a new integral over here, and hopefully that new integral allows us to get something that we can anti-differentiate. The key is to select the dv that is the most complex of this that we can integrate. Now, in this particular case, it doesn't really matter because both e and cos are equally complex, so we're just going to arbitrarily choose cosine as our dv. So I've selected my dv, I integrate this so that I generate a v term. Okay, and then I need to choose a u term, is the remaining part here. There's my u, and I'm going to integrate or differentiate this to generate my du. So the du part is just e theta d theta. Okay, so putting it into my formula, I end up with uv, so it becomes e theta, v is sine theta, minus the integral v du. In this case, I'm going to end up with e theta sine theta. So v is my sine theta, and du is the e theta part of that. Okay, so at this point, it looks like I'm still stuck. So I'm going to reapply integration by parts. So this time I'm going to choose sine again, and that becomes my sine theta d theta is my dv. So again, I want to choose my dv as the most complex I can. So dv is sine theta, and v is the integral of that, which is negative cosine theta. And it's important to keep track of your pluses and minuses. So my u works out to be e to the theta, so works out very similarly to the above. Du is e theta d theta. Okay, so I have all my parts now, and so I'm going to end up with my original integral e theta cosine theta d theta, and that's going to be equal to uv. Okay, so I need to make sure I have my original part, so I'm maybe just going to box this in. This is the part, the new integration by parts piece. Okay, so my original part was e theta sine theta minus, and this now represents the new integration by parts. So I get uv e theta negative cosine theta. Okay, so that's going to end up being plus e cosine theta minus the integral of v du. So that e, so I end up with e theta, the cosine theta is my v, the d theta came from the du, and then I had that extra negative cos, so I'm going to make that plus. Okay, so really we have to be careful of our signs here. Now, the problem is that I've kind of run into the same as what I started. Now that could seemingly be a problem, but actually it's a benefit because what we're going to do is we're going to be able to write that expression on the left side of the equation, and we can actually solve this algebraically. So it looks like this. I'm going to work out all my signs first. So e theta, sine theta, expand out the brackets of plus e theta cosine theta minus, okay, so this then we have a minus plus, so this becomes minus the integral of e theta cosine theta. Now, this looks like we really haven't gotten anywhere. However, what we can do, and because that's a minus e theta cosine theta, I'm just going to highlight this, that minus there allows me to move it to the other side and group it with that expression. And when I do that, so I'm going to add it to both sides, I have two of those expressions, e theta cosine theta d theta equals all of that. And now I can actually, since I'm solved with what I wanted to really find was, the value of the e theta cos theta d theta. I just need to figure out what's on the right hand side and divide by 2 to get rid of the times 2. So e theta sine theta plus e theta cosine theta. Okay, and then we just divide both sides by 2 and we get our answer. So we divide by 2 and divide by 2, and I end up canceling out these terms, so there I have my solution. So this represents the integral of e theta cos theta d theta. And we solve this not by actually undoing the integral, but by actually regenerating the exact same integral and solving it algebraically by moving it to the other side.